Okay, good morning. Welcome everybody to blazing hot Arizona. My name is Benjamin, and I'll be talking to you a little bit about what Robert already referred to in his keynote speech on Monday in the area of advanced analytics. So let me start by telling you that I'm from Belgium, and to make my way all the way here to the Global Summit, I unfortunately couldn't take the plane out of Brussels Airport, which is very close to where I live, because there were two kind of bearded brothers, Islamists, who decided to mess up our airport. So I had to take the train. When I was sitting on the train, I had to take the train through Paris, and then from Paris I flew here through Washington. So while sitting on the train between Brussels and Charles de Gaulle Airport in Paris kind of has one stop. So when I was sitting on that train, for the first part of the journey, there was nobody in the carriage. I was almost alone. There were like two other people. So I thought, hey, they're not doing a terribly good job at kind of scheduling how many carriages they need for this drive. But then the train stopped in Lille, which was about halfway, and then suddenly there was like this gigantic mass of people who also boarded the train. And there were about 2 spots left in the carriage that were not taken. So then, with my fish-like memory, I thought, hey, they're doing such a good job at scheduling how many carriages they need for this leg, because it's very well estimated. And then I was wondering, how do they estimate how many carriages to put on each line? Well, that's probably because they're doing some sort of meaningful analytics. And meaningful analytics, that's something that we all know. That's you measure something along a particular dimension, and then you try to visualize what's happening, and then based on that visualization, you can see like, okay, on this particular route, there's this many people, so I can put that many carriages. And if you think about trains, so if you are running a train company, anybody in the audience running a train company? No, not too many. But if you're running a train company, you could look at dimensions like your route network. Like this is the high-speed rail network in France. This is Brussels, and this is the center of everything, also known as Paris. And you have 230 different train stations. That's reasonable. You could even picture a table that has 230 rows and then numbers or nice bar charts that say how many people board the train at every train station. So you've got measurements, you've got dimensions, and you can organize those into nice graphics that kind of visualize things. And then if you are a director of the train company and you're sitting at your desk and you can see the pie chart or the bar chart moving, and then you say, okay, I want to have this many carriages there and this many carriages there, and that's it. That's kind of data-driven decision making. So with a bunch of dimensions, you can get by and do some analytics. So that's for the train leg. Then I took the plane, and when I finally arrived in Phoenix, I had to take a taxi. So I was not sitting alone in the taxi. I had kind of run into a colleague in the meantime. But for scheduling how many taxis to put on a particular route, that's a little more difficult. So let's take a look at the route network for taxis here in Phoenix. How many stations do you see on this picture? Well, taxis don't use train stations. They don't have fixed locations. So suddenly that easy data set, that easy dimension of 230 different stations becomes a little more complex. There's no fixed routes. There's no fixed times at when they start. So suddenly your picture of, okay, I'm going to take some data, I'm going to create a bar chart out of it, I'm going to put it in a pie chart, and I'm going to visualize it, and then the decision maker can immediately see, can get the insights that he wants. That is not as practical. And the reason for that is that there are a lot more dimensions in this little problem. Obviously, trains also have more complexity to it, but then you have so many dimensions that you just can't fit it all in a pie chart. That is getting way too complex. And in those cases, there's still obviously data to be used. You can still try and make you still want to base your decisions on data. You're capturing the data, so you'd better use it. But how do you know what the dimensions are that make most sense? Do I have to look at, for example, the taxi rides or the average tip that I get? based on the time of day? Do I need to include the weather? Do I need to include what the demographic information of the pickup location is? Does the destination location matter? So you don't know which dimensions to choose or which combination of dimensions to choose to kind of visualize your information in a meaningful way. So wouldn't it be nice if software could take care of that? Wouldn't it be nice if there would be software techniques that automatically identify what combination of inputs are good indicators or have good correlation or have a good predictive value for a certain output? Well, that's what we're going to talk about. That is what is called machine learning. That is the discipline of, or the science of creating systems that learn from data, and that learn from data in order to help you make decisions, in order to give you a model that predicts or models what's happening in the real world, so that you can make a decision, or that you can even let a system automatically react to something that's happening in the real world. So that's machine learning. But let's look at it perhaps just for a second at a more theoretical way. So this is a kind of a definition for machine learning that Tom Mitchell designed. And the idea of that, the theory that he had was that if you have a task T and you have a way to measure performance called P, so this is the P-axis, and you and you have a system that kind of makes decisions or kind of executes this task T based on experience E, then Tom Mitchell says that your machine is learning, ergo the definition of machine learning, if as experience grows, performance goes up. It sounds fairly trivial, but it's obviously challenging to create systems that actually do this. But that's the general idea. So the more experience you have, the better your model becomes, and the higher your performance score will be for whatever task T that you are trying to achieve. So that is a definition of machine learning. Now, machine learning is not a simple thing, obviously. There's a lot of different types of problems that machine learning attacks. It tries to approach. And let's go and take a look at kind of a very rough taxonomy of machine learning problems. So the most common ones are supervised learning problems. Supervised learning means that you have data that contains inputs, and that contains features, and most of those are the inputs to your system, the inputs for your model, and one of them is your target. You want to build a model that predicts the target value, the output value, based on all the other input values. For example, you want to predict what the average tip is going to be for your taxi rides based on your pickup location, your destination, the time of day, day of week, season, and a lot of these other variables. So that's a supervised learning problem. Specifically, the fair prediction thing, if it's kind of a continuous value that you're trying to predict, that's a regression problem. You're trying to create a formula that predicts a numerical value. If you're trying to predict whether he's going to pay in cash or whether he's going to pay with credit card, then it's a classification problem. You're trying to classify your case, your observation, based on the inputs that are there. I won't say that supervised learning is an easy thing. Creating these models, there's many different algorithms out there, very complex, very advanced algorithms. But measuring the results, measuring the quality of your model is an easy thing, because you know what the output is for your historical data set. So you can say for the regression problem, okay, my average error is this much, a numerical value. You can't kind of argue about that, so that's okay. Also for classification, you know whether it's right or wrong. You can express that in false positives, false negatives, true positives, and true negatives, and you can easily kind of quantify the quality of your model. So that's supervised learning. Second group of use case, second group of problems is unsupervised learning. Those are a little more challenging. Those are, for example, can I group my taxi rides in a way that is meaningful based on their characteristics? Can I, for example, identify whether I can split up my my audience or my customers based on their buying pattern? And can I find, and then afterwards, after you've tried to automatically let the computer decide what those categories are, you can see whether that kind of corresponds to particular segments, whether there's, for example, indeed a correlation between how you split up your customer audience and their age or their family size or where they're actually living. So that's what's called clustering, and clustering is a classic example of an unsupervised learning problem. In an unsupervised learning problem, there is no right or wrong. There is no good, you don't know whether you have the right solution because there may be many right solutions. So for unsupervised learning, you have beforehand, you have to kind of identify what the quality metric is going to be that you're going to use to assess the quality of your model. So imagine the clustering example. We'll get to that, to a practical example later in the session. Imagine that you're trying to kind of group points on an XY map in 3 groups. Then you could kind of come up with some sort of measurement that says that the average distance to your closest group or the closest center of your group, that is going to be your measure of success. The higher that number, if that number becomes higher, that probably means that your points aren't really well chosen. But if that number is really small, that means that your points really represent kind of the center of natural clusters. So that's unsupervised learning. You don't know what you're going to get, but you try to make a model that kind of gives you a good impression, or that gives you a good a good model of reality. And then the third, and maybe fanciest of these 3 types of issues, three types of problems, is reinforcement learning. In reinforcement learning, again, there is no real right or wrong, but you try to learn on the go. This is the closest to artificial intelligence that it gets. So, for example, if you're trying to learn, if your computer is trying to learn a game by playing the game. So if your computer is learning chess by playing chess players, and if he loses, he knows that he probably made a few wrong moves. If he wins, he knows that he probably made a few good moves. And by just playing more and more and more games, you learn. So you get reinforcements along the way. Another example of reinforcement learning is the slightly more theoretical problem of the multi-armed bandit. We're not too far from Las Vegas here, and a couple of customers from Belgium are going there this afternoon. So in Las Vegas, you've got one armed bandit. So a slot machine, you just pull the arm and then you lose money. And in very rare cases, you may even win a little bit of money. So there's a probability distribution that says how much money you're going to win by pulling the arm. Now imagine that you're in Vegas and you're sitting in front of an entire row of these machines. The multi-armed bandit problem is a problem in which you want to maximize your returns, obviously, by learning which machines to play, because every machine has a slightly different probability distribution of how much you're going to gain. So the multi-armed bandit problem is kind of finding an algorithm that tests the machines, tries to learn their probabilities along the way, and eventually find out which combination or which sequence makes most sense to kind of maximize your returns. I think that's a very theoretical problem, that you can maximize returns in a gambling situation. But anyway, so that's a classic academic example of reinforcement learning. So we've seen 3 different categories of problems that you can try to approach with machine learning. Now, as I mentioned, there are many different algorithms to get to these, and every other month there are a ton of publications from academics who find yet another algorithm that is very appropriate to regression problems, or yet another algorithm that is very good for classification problems that involve psychological or behavior, human behavior. Or you have or they come up with a new algorithm, a clustering algorithm that is extremely appropriate for clustering the distribution of bacteria in a particular type of place, whatever. So what I want to get at is that these algorithms, they all have characteristics that are specific to, that get more and more specific to a particular type of problem. So if you look at the list, if there is such a thing, of machine learning algorithms, that will be a gigantic list of algorithms that sometimes are very similar to one another, but have something that's slightly different. So knowing which algorithm to choose to approach your problem is a challenge. It's a science, and it's called data science. And the people who do this are called data scientists. So they are somewhat different from developers. Any developers in the room? Any data scientists in the room? That is also representative for the distribution in real life. There's many more. Data scientists are a rare breed, but there's a lot of marketing about them, and they're superheroes and they have superhuman powers. But apart from the superhuman powers, what their specialty is knowing which algorithms to choose from, or maybe to put it differently, which algorithms to try, and which ones to try next, and which ones to try thereafter. Because that's probably the most significant difference between developers and between data scientists. If you're developing something, you've got a goal, you've got a certain requirement that you want to implement, and at a certain point in time, about 3 times as long in the future as what you originally thought it would take, it will be finished, and it's done. And maybe there's a bug or two, and you can fix them, but it's going to be done. You implemented the requirements. Whereas in the case of the data scientist, you can build a model, and then you can build another model, and you can build another model, and then the next one will be maybe just a little better. And then if you go back, if you remember the definition that Tom Mitchell gave with that graph, and then maybe the next month you have more experience, you have more data to base your model on, so you can just build your model once more, and yet another time. So you will build and build and build your models over and over again, and you will try new algorithms, and some algorithms will give better results, and other algorithms will give worse results. But it is an iterative process to boot. Maybe a few other difference between these two personae is that a developer typically knows how to use different programming languages and works with patterns, and you know a couple of development patterns, design patterns that work well to address particular kind of sort of high-level requirements. Whereas the data scientist uses a bunch of different tools and tries to use and knows algorithms and knows which algorithms work for which types of problems. Also, developers do data modeling. Data scientists, they just kind of fiddle with data to make it fit the required inputs for every algorithm. So they're always kind of messing around a little bit with the data to make sure that it works well for the particular use case they're having. So they're really different people. They're somewhat converging because of the tools that they dispose of, but the mindset is still somewhat different. So let's take a look at a couple of examples of tools that these data scientists use. Some of these you may recognize. So there's a couple of like SAS and SPSS that have been around for ages. They're very well recognized. They're also very expensive. And they're very specialized to the sorts of things that data scientists do. They're very much tailored to what machine learning is all about. The others are as well, but for example, R, KNIME, and then Scikit, or however you pronounce it, is a Python library of algorithms. Those are open source solutions. Some are half open source, but you can still buy support for it. So there's a variety of tools to choose from. And so, for example, SAS is an established product. It has a lot of libraries that are specific to particular industries or problem types. R is an open source product. It has a fairly simple programming model, and because of that, there's thousands and thousands of algorithms that have been implemented by people in the open source community, by academics, that are contributed to the R CRAN, it's called, the Central Repository, and then something with an A and an N. So there's a wide variety of things to choose from in this world. Now, let's go back to our description of the taxis. Imagine that you're not living in Brussels with just a handful of taxis, half of which are on strike, but imagine that you're living in a real city that has lots of taxis, that has lots of data. So, for example, you couldn't just measure where you're picking up your customer and where you're kind of putting the destination where your customer wants to go to, but you could perhaps also try and track the route that he's taking. So for example, at 30-second intervals, sample your XY location and track that as well. You could factor in the weather, you could factor in the traffic situation. So all these kinds of things could be additional inputs. But it adds up, not just in numbers of dimensions, but also in numbers of data points. And if you have that for an Uber-like amount of cabs, it becomes very unwieldy. And the tools that we just saw start having problems. So then we're no longer talking about just machine learning, but we're talking about machine learning on big data. And you need to make sure that your tools can also stomach these vast amounts of input data. Now, how can you approach that? So the most classic and possibly easiest way to deal with big data is by using vertical scalability. So if this machine is not big enough anymore, you just go to the shop and you buy a bigger box. If that isn't big enough anymore, then probably once you're at this size, the salesperson will come to you rather than you going to him. You just buy yet another bigger machine. But this is that's a very expensive way of scaling. Also, if you only need it kind of for a limited amount of time, and actually after a particular experiment, you would like to go back to this machine, well, you just bought this one, so you can't go back. So it's not a very flexible solution. But it is convenient because your algorithms don't have to change too much. Whereas if you can split them over multiple cores in multiple processes, they can still access the same memory. So they can use shared memory. So that's still kind of reasonable to implement if you are a data scientist tool developer. So this is how many of those data science tools that we just saw work. So for example, SAS, you can buy SAS licenses for bigger boxes. You can buy SPSS licenses for bigger boxes, and that works well. But it's somewhat still a vertical way of scaling. And for R, it's actually worse, because the advantage of R was that it was very simple, which also is a disadvantage because it can't take advantage of multi-process things as easily as these others. So it's kind of a two-edged sword. So the preferable way to scale is obviously horizontal scaling. Is you start from a small machine, and if you need more processing power, you just buy a couple more small machines. Possibly you just fire them up, and as they're waiting for you in the cloud. And if you need yet more, then you go to you just add more nodes to your pool. That sounds obviously straightforward and sounds very beautiful, but it is much harder to implement from an implementer's point of view, because your data is going to be spread out, your memory is going to be spread out. If these need to communicate with one another, you need to make sure that your network protocols are okay and that the communication is efficient. So for example, if you want to calculate the sum of a particular column in your data set, calculating a sum in a distributed environment, that's fairly straightforward. You just calculate the sum on every individual node, and then you add those numbers up, and then you have the overall sum. Now, if you want to calculate the median of a data set that is distributed, it already gets a lot more complicated. It's a lot more hassle to kind of implement that in a meaningful way. And guess what? Machine learning algorithms are often more complex than calculating a median. So developing machine learning algorithms in a horizontally scalable manner is a challenge. It's very complex. Getting back to the scaling story in general, there's one platform that has been exceptionally successful in this in the past 5 to 10 years, and that's it has a horribly ugly logo, but it's called Apache Hadoop, and you probably heard about it or have worked with it. Anybody who has worked with Hadoop? Okay. So at the very core, what Hadoop offers is HDFS, Hadoop Distributed File System. It's a distributed way of storing your data. So rather than storing, it just abstracts for you the fact that your data is not sitting on just one hard drive, but sitting on a lot of hard drives in a clustered environment. On top of HDFS, Hadoop also includes Yarn, cluster management software, and MapReduce, which is a development paradigm that allows developers to kind of code approaches to for example, calculate the sum or the median in a distributed environment, or make more advanced things, but it's a developer tool. So once again, what are the advantages of such a solution? Obviously, the scalability. You can easily scale it up, or if need be, scale it down. It's an elastic platform, so if your requirements or if your load drops, you can just free up a couple of nodes, and the cluster will will be able to support that. And then a third advantage of a platform like Hadoop is that it's very resilient. It's very robust. So one of the key parameters if you're setting up your Hadoop cluster is your replication factor. So every partition of data, how often are you going to store it? Because if you store every partition of data more than one time, if one node fails, you will always have another copy sitting somewhere else. So that by having a replication factor of 2 or 3 or even more, your system is much more robust. And possibly algorithms that run on top can take advantage of that. Why is that interesting? It's interesting if you're trying to economize on the quality of these machines, or if you want to use commodity hardware that does not have the uptime guarantees of a mainframe, then you can have, at a much lower cost, have a much bigger overall system. So that robustness is also an interesting characteristic of an horizontally scalable system. Okay, so let's go back to our two personnel, to our developer and our data scientist. How will they take advantage of a horizontally scalable infrastructure? So the developer will think of, okay, I've got my Hadoop, I've got my MapReduce, so I can start to develop something that's resilient. So if one node fails, my algorithm that would take a couple of days to complete will still finish. So I can develop a particular algorithm on top of this infrastructure. There is another Apache project. Hadoop is an Apache project, as I forgot to mention. And that's called Apache Mahout, M-A-H-O-U-T. There's probably a better way to pronounce it, but that is a library of machine learning algorithms that were implemented on top of Hadoop. It's a broad library, but it's very diverse. Every algorithm was implemented, many algorithms were implemented by completely different people, starting from scratch, starting from just HDFS and the MapReduce paradigm. So they are very, very different in approach, and they are also very different in quality. So there's some skepticism about the quality and the comprehensiveness of Mahout. So for a data scientist who doesn't really like to develop, because you can't develop and develop again and again and again, as what they prefer to do, it would be much more interesting if they would have access to sort of an abstraction of the data, and that they could then use their tools, base their algorithms on an abstraction that kind of takes care of the fact that it's distributed somewhere down below. And that if you ask for the sum of a column of your data set, or if you want to apply a particular function to a number of columns in your data set, that abstraction takes care of forwarding that in an efficient way to all your different nodes. So that would be a resilient distributed data set, an RDD. I didn't make that acronym up. It was made up by a couple of guys at UC Berkeley in 2009, and then since 2009 they've been publishing very interesting papers about this, and they have published their implementation of RDDs in an Apache project called Apache Spark. So Apache Spark is an infrastructure project that does pretty much the same as what Hadoop did for distributed storage, but Spark does it for distributed computing. So where Hadoop takes care of storing your data in a distributed environment, Spark takes care of doing something with that data in a distributed environment. So you could think that, oh, that's what MapReduce did, didn't it? But, and that's indeed the case, but Spark offers a much nicer, much more abstract interface to it and has a large number of optimizations that it does automatically for you so that you don't have to care too much about the actual implementation, which you had to write yourself if you were doing it with MapReduce. So what does Spark do? So Spark as a framework offers this RDD abstraction over data. The data can come from Hadoop, obviously. It can come from a database through JDBC. It could come from InterSystems in the near future being the demo in a couple of minutes. Or it could come from like cloud storage systems such as Amazon S3. And how do you access Spark? You can access Spark natively through Scala and, or Java, or you could use data frames. You could use this RDD abstraction in Python or in R. So you can choose which tool you like. And whereas the top two here are typical development tools, Python and R are more tools that belong to the world of our data scientists. So it starts getting more familiar for our data scientist friends. So let's take a closer look at how Spark actually works, or what it looks like if you start developing code in Spark. So this is Scala code. Anybody who knows Scala? I'm not raising my hand. So Scala is a language a bit like Java in the sense that it's also object-oriented. It also runs on the JVM, but it is more abstract. It's more fuzzy, if that's a right term to use. And it's much more powerful because you can do a lot more in a lot less lines of code, which is what we like for people who like ObjectScript, like to do things on fewer lines of code. By definition, no exceptions possible. So first line, what's happening? So we're creating a text file abstraction. We're creating an RDD on top of a text file that we get from a certain address. So S3 is Amazon S3. So you've got your cloud storage space. You refer to a text file on your cloud storage space. And then we're going to apply a few operations to our RDD. We're going to map an operation to it that will actually split every line. So typically, the abstraction of a file means I'm going to have one row that represents each line. So we're going to split every line into words by splitting on every space. So that's the first operation we apply to our RDD. The second operation that we apply to our RDD is that we're going to map every row that currently has one column, which is a word. We're going to map that to a tuple, to a pair of a word and a one. And then in a third operation, we're going to reduce that information, and we're going to just group by our first column, so our key, and we're going to just add up the values that are on the second position of our RDD. So we've just created a word count or a word frequency table for our data set. So I've got my variable counts, and what has Spark done in the background? Nothing at all. Spark is a very lazy platform. So lazy meaning it doesn't execute anything until you really ask for results. And that's very powerful, because if it would have started to map this operation when I wrote down the operation, it would have gone out to Amazon and started to fetch all the data and then started splitting that. And then it would have then converted, in the second operation, it would have again gone through all the nodes of my cluster to go through every partition, go through every row, and transform every row into a tuple of words and ones. And then upon the third call, it would have, again, a third time gone through all the data to kind of create that aggregation, to create that summation. So that's not very efficient. That's why the laziness is really helpful, because up to this point, Spark has done nothing. It has just remembered what you asked it to do. It's only when you really ask for a result, when you want to show something. So even here, on the second line, where we're sorting our results and where we're asking it to only kind of give us back the top 10 results. So this is going to give us back another RDD that contains only the top 10 rows of what came before. So even then, it hasn't done anything. It's only until the very last moment, only when you really ask for results, that it's going to look at everything you've asked it to do so far It's going to compile that into optimized code, and it's going to send that code out to all the different nodes in your cluster so that they can start operating. So that obviously has the advantage that things that could have been done in one go are done in one pass, and that makes the system a lot more efficient, and you don't have to think about it up front. You can write this on 20 different lines, and still Spark will only start doing it when you're really asking for the results. So that's the flexibility and the kind of automated optimizations that you get from Spark. Now, Spark by itself is obviously kind of still a relatively basic or relatively infrastructure level architecture, but it comes with a couple of libraries that implement specific functionalities that help you deal with particular types of problems. So for example, Spark Streaming is an extension of the Spark framework that allows you to deal with streaming data. So for example, Twitter data, there's no table that contains all tweets. No, they just keep coming in. Once you've read 10, there's already 2 new that have appeared. So Spark Streaming helps you address those sorts of use cases. Spark SQL allows you to kind of have a slightly higher level abstraction of RDDs that has metadata, so that your RDD behaves like a table. That's very nice, because you can query tables. You can apply SQL against tables. So suddenly you can apply SQL against Spark data frames that underneath are actually files that are sitting in your cloud storage. Graphics is a library that helps you deal with graph data. And then finally, and this is obviously where we wanted to get at, Spark ML or MLlib is the machine learning library. So a growing number of machine learning algorithms have been built on top of the Spark framework, taking advantage of that data set abstraction. So far, so good. I've talked quite a bit about products that are not sold by InterSystems, products that are not sold by anyone, because Spark is free. It's an open source project. So what are we doing? What is InterSystems doing in this area? At InterSystems, we want to provide you with a platform that helps you deal with data, that helps you store data, that helps you query data in an efficient fashion. And as Robert has explained in his keynote on Monday, we're making this platform horizontally scalable. We're doing a lot of work in the background to make sure that you can have your tables spread out over different machines in a sharded environment, so that you can take advantage of the implicit advantages of a horizontally scalable platform. What we're doing now is by integrating with Spark, we also want to make sure that you can take advantage of that data in a more or less programmatic fashion, so that if you do not want to use SQL, but if you want to do something else, if you want to do some machine learning, that you can take advantage of data that is stored on your cache platform. And how are we doing that? By making sure that if you want to kind of bind your RDD or your data frame to a table that is distributed over your cache cluster, that every Spark node, every Spark worker process on a node is only talking to the data in the cache shard or in the cache partition of your table that's on the same node, so that there's no unnecessary communication between those nodes. That is really kind of a well-integrated, a tightly integrated system that maximizes throughput and maximizes efficiency. Also, if you're asking your system to, if you're asking your RDD to kind of your data frame to only give you back 2 columns and then filter by a particular where clause, we're going to make sure that that where clause is pushed down into cache, so that cache will read from disk the least, only the rows, only the fields that you're actually asking for, whereas in the case of if your data is stored on Amazon S3 or is stored on Hadoop, you would be reading the whole file from disk and then in memory in Spark trying to kind of throw out the things that you're not interested in. We can do that at a much earlier moment so that you can have even better performance in your system. So how would that look? So we're also going to work with such a context object, and you just attach your RDD to a particular sharded table, and then you can just start working with it. So I can, for example, add a column, I can cache a column, and I can feed it into this machine learning algorithm. But I'm doing not so well on time, so let's maybe now jump to, because the presentation is at the end anyway, so let's jump to a little bit of a demo. So what I have here is a notebook. So this is also an open source tool, a utility. It's somewhere between a command line and an IDE, such as Atelier. And it allows you to kind of document your code in a much nicer fashion, and it presents nicely. So what are we doing? We're importing a bunch of rows. So this first demo is running locally on my machine, so this is not yet attaching to a cluster. And I'm reading some data from a CSV file. And the data that I'm reading is actually 4 million, 20,000 out of 4 million taxi ride details. And here you can see the schema. So I've got every taxi ride has a trip ID and then a number of metadata fields. And then the most interesting field that I've been looking into is a polyline. So that's kind of a number of coordinates, a string that contains a string of coordinates, a sequence of coordinates that represents the route the taxi took in Porto. It's Porto in Portugal. That's where the data's coming from. So here I'm loading the data, I'm applying a filter against it, I'm limiting the result, and Spark hasn't done anything because I haven't asked for results. So now, being a data scientist, I need to prepare my data a little bit, so I'm going to create functions that parse my polyline into an array of coordinate pairs, and then I'm going to go through that array of coordinate pairs, and I'm going to calculate the distance. So still, my Spark hasn't done anything. I've told it to cache the data, but it's only going to cache the data when I ask it to calculate it the first time. But when I ask it to calculate it the first time, it's going to keep a copy of it around in memory in case I want to access the data again later on, which I will do as part of the clustering that I want to do. So we can map this on, we can plot this on a map with a little bit more patience. So now is the first time when it really starts to do something, because I've asked for the results. So now it's going to push the commands to the worker nodes in my very local cluster, and that's what it's doing now. And then at the very end, we'll see the result. In the meantime, I'm already going to launch the second demo because it takes a bit of time. Now, this is going a little slower than expected, but anyway, I'll get ahead of it. We'll see the map in a second or two. There we go. Poof. So this is Porto in Portugal, and you see a nice plotting of all the starting points for the taxi rides, and then the size of the circle is in line with the total distance traveled. So this was kind of a secondary airport, so a long trip from here into Porto. So now I'm going to gear up for my clustering operation. So I first transform my data into the input format, the actual data type that's required for my clustering algorithm. So I'm transforming it into a vector array. And then when I have that, I can open up my k-means clustering algorithm and fit it against my cluster data set. So let's plot that on a map. And let's see these very surprising results. So I have 3 cluster centers of my, because I asked it to calculate 3 clusters, but one of them is here, and there is no island underneath, and definitely not an island that's part of Porto City. So there was some dirty data in my data set, and because clustering algorithms try to find clusters that best represent your data, that have the kind of the least distance, the least aggregated distance to those cluster centers. That's why it ended up there. So that's a bit of a bummer. So but this is I deliberately kept the wrong record in. Not because it's not too easy to find such a record in 4 million row CSV file, but also because it shows what data scientists do on a daily basis. They try, they err, and they try again. So it's just a process of constantly cleaning up your data. So there was just like a nice distribution over these 2 first clusters and then one over the next one. So Then I excluded it and I calculated it again, and now this looks much nicer, and I can plot the results. And again, on a map, color-coded. And now this looks a lot more like it. So now if I zoom in, I can see that it indeed made sort of a meaningful grouping based on the first, the pickup location. So this is something that this is quite obvious, obviously, that they will be nicely, that these clusters will kind of remain close to one another on the map. Now let's make this a little more complex by also including the destination location in our clustering algorithm and the total distance traveled. And if we then plot that on a graph, it will, you'll see that there's still a couple of outliers that I would like to look into that are pretty much off the board. But then maybe because they, what could be an interesting characteristic where only a couple of records fall into is if you make a very large round trip, because then your destination and your origin are very close to one another, and but your distance is very, very long. So that would be, for example, a reason why this category of records would be far off from the rest. So, and here you can see that now it gets a little more complex, and we would need to look more closely into why they are organized in such a way. Okay. In the meantime, I've launched a system that's running in Cambridge, in our HQ. There we have a cache cluster, so a sharded environment where we have four machines that each contain the shard of one. Oh crap! And that so where the data is running in one machine, and then actually I should have been seeing some of the Spark metadata that shows me what's running. So on every shard node of my cache cluster, I also have a Spark worker node that's running, and that's doing a similar but not identical clustering operation. And then at the very end, it will kind of show me the results of the clustering. So here, this is a more artificial data set of 10 million points that were centered around 8 points in an XYZ plate. So all the either coordinate 1, 1, 1, coordinate 1, 1, minus 1, and so on. So we generated 10 million data points that are randomly around those, and then we try to apply our clustering algorithm against those to kind of find back these 8 points. Okay, I'll let this run for a little longer. It's a bit of a pity I can't show you the nice visualization, because it shows where the data is running. No, it doesn't feel like it. Ah, there we go. Ah, this is it. So active jobs. So here, it's where we started the conversation. Eventually, you just want nice visualizations to show to your boss. So that's what we. So this is a visualization of what what operations Spark is actually doing, which intermediate RDDs it's generating under the hood that we didn't have to worry about. So this is what you would have had to implement manually if you would have done this on MapReduce, but it's all kind of part of the kit. And this is just one of the tasks that it's doing. Okay, so much for my presentation. I've gone a little bit over time already, but any questions still about machine learning or what we're doing in this area? Yes. So there is, Spark comes with a JDBC connector natively. What we're doing is creating another connector that takes advantage of the shard master metadata that we have to know how we can exploit locality. And then at this point, we're still using JDBC to connect to the individual shards to get the information. So then every worker node is using JDBC to get the data from its local table. But eventually, we want to kind of get JDBC out of the equation altogether and use the new Java integration that you may have heard about at yesterday's unconference. Okay, I won't take any more time from the next presenter who needs, so that he can start setting up. If you have any further questions, don't hesitate to ask them on Slack or on the developer community, or just grab me if you see me pass by. Thank you.